So I will speak about the recent works, which is partially published only, and it will concern the convolution equations on Lie groups. I will start with the well-known convolutions, and then we'll tell you about convolutions on groups, some general facts. Then we'll introduce some new spaces, which I call generic Bessel potential spaces, which are much better adapted to the convolution equation, for the convolution equations on groups. And then I will demonstrate it on the example that they are really very good adapted, these spaces, generic Bessel potential spaces. And after that, well, I will demonstrate several Lie groups. Some of them seem very strange, and it's difficult to imagine that they were Lie groups, but they are Lie groups. And we expect in the nearest future that we will find many examples in applications which will be handled by these methods. So, first of all, it is very well known, these convolution equations of when the kernel depends on the difference of arguments. It's a classical convolution equation where the Fourier transform plays important role. The most important and most outstanding property of such convolution equations is that if you take Fourier transform of this equation, it becomes multiplication by the independent variable. And they are solved just, you require that the symbol is not zero, but sometimes it's not enough. You should require that the inverse is also convolution, bounded convolution. I will give you some example of Igari, which shows that not all convolution operators which are which have elliptic symbols are invertible. Okay. Another example of such convolution equation is the Mellin convolution equation. When we are on the half axis, and the convolution equation, kernel of the equation depends on the ratio of arguments. Then the Mellin transformation plays the same role as the Fourier transform in the first case. Oh, I forget to say that in the case of convolutions on the whole axis, the differential operators, usual differential operators, are convolutions, also convolutions. And in this case of Mellin convolutions, so-called generic differential operators, which are convolutions, are the operators which are derivative multiplied by the independent variable, t d dt, or such operators are also convolutions, t in power k, d dt in power k. They are all convolution operators. And you can handle the integral differential operators, take Mellin transform of this equation, and again you will get the multiplication by function and can investigate easily what is the unique solvability conditions and so on. Now, what is the common feature of these two equations, which I demonstrated here, that they are convolutions. They are convolutions on groups. First equation on the whole axis on Rn, they are group, underlying group is Rn, which is group under addition of elements. Second example is the convolution on the group, where the group is multiplication with respect to the multiplication half axis. The group with respect to multiplication of elements. And all elements in groups, as you know, they must have inverse. But in this case, the inverses also exist. Then we have the whole Fourier transform there, which in second case coincides with Mellin transform, and so on and so on. And the convolution equation in this case is, in such a case, is simply defined by taking Fourier transform, then multiplied by function, which is called symbol, and taking inverse Fourier transform on the group. So now about group. We have now group, which means that we have, I think I missed the previous slide, but it's very difficult. Yes, two equations. Yes, common feature that they are the equations on the group. Well, now consider a general group. If we have group, that means that G has the manifold structure. Then on G is defined the group operation. Then there exists this neutral element. There exists inverse. If we have these conditions, if we have such group, we will have then automatically a Haar measure on this group, which is unique. We have Fourier transform there, and inverse Fourier transform. So the whole harmonic analysis can be developed for such groups. And, well, here is the example. Here is in the first case, it was the sum, which makes the group Rn group, and the multiplication, which makes the group R plus half axis. Okay. Oh. Yes. Well, now we define the general convolution equation on the group. How it is defined? We take the Fourier transform from the function, from the Schwarz space of fast decaying functions, then multiplied by the distribution, Schwarz distribution, A, which is the dual group to dual space to the Schwarz space of fast decaying functions, slowly growing functions, well, Schwarz space of distributions, and then take Fourier transform, inverse Fourier transform. So it maps a Schwarz space to the distribution Schwarz space, this operator. And if this operator is bounded in LP space, such symbols are called LP multipliers. And the class of such symbols are partially described. In case of L2, you know, perhaps many of you know that in L2 spaces, these L2 multipliers coincide with simply with bounded functions, but in LP there does not exist a full description, but what is known, the functions of bounded variation in the case of the axis, functions of bounded variation, functions which are Fourier transforms of L1 function, they give us the multipliers in LP, in all LP. But what is strange? Yeah. Well, okay. Well, in Rn we can show that functions which are constant, piecewise constant on polytopes, piecewise constant functions, they are multipliers in LP, in all LP spaces. And well, about invertibility, we denote by PC, PCP, the closure of the piecewise constant functions in the norm of multipliers. I mean, the operators in LP with the symbol A, convolution operators with symbol, we close. And we have now multiplier class MP and PCP, which is the closure of this piecewise constant functions. And having this, we can formulate theorems about unique solvability of convolution equations. Again. Yes, convolution operator is for the invertibility of convolution operator, it is necessary condition that the symbol is elliptic. Well, determinant of the symbol, if it is metric symbol, determinant of the symbol should be does not disappear. But this is not sufficient condition if the symbol is from MP, I mean multiplier. But if it is from PCP, then it is invertible if and only operator is invertible if and only if symbol is elliptic. And here is the Igari paradox. I call it Igari paradox. Igari had found the even continuous functions which are multipliers in LP, pair different, in all LP, in LP when P is fixed, but in L2 too. And, but the inverse to it, it is elliptic, even more than one everywhere, but the inverse to it is not multiplier. In L2, yes, but in LP, not. So it's, let us call it Igari paradox. So we need this PCP class to have the necessary and sufficient conditions about invertibility. Okay. Now I want to introduce, first of all, the generic differential operators. We have group. And on the group, we have generic differential operators. What they are? They are convolutions which have symbols, these symbols, the same symbols as in LP, which symbols have minus XCK. These operators we call generic differential operators. What these operators are? We have Lie group, and Lie group, and to Lie group is associated Lie algebra. Lie algebra consists of vector fields. Vector fields. And these vector fields generate, of course, the differential operators. Those generic differential operators are exactly these operators generated by the vector fields from the Lie algebra. And they are natural differential operators for these Lie groups because they are convolutions. Such generic differential operators for the axis, for Rn, is the coordinate differentiation. But for R plus, these differential operators are derivative multiplied by independent variable. This was noticed first by Kondratiev, and he introduced also such spaces, which I called in my earlier works also Kondratiev space, Bessel potential space, with the help of generic differential operator multiplication by T. And for the generally for the Lie group, they always have their own generic differential operators, and we have to pay attention and to take into account these operators. And we have generic differential operators, and we can consider now the integral differential operators, which are convolutions on Lie groups. What is convolution on Lie groups? You take element, multiply, and take the group operation over X, group operation with Y minus 1. And add these generic differential operators. This is integral differential operator on the group. And you take the Fourier transform of this integral equation, and you arrive again to the multiplication operator, where you have the symbol, and ellipticity of symbol is necessary condition for the invertibility of such operator. And the sufficient condition is, again, you should consider only PCP. A bit more, you can consider a bit wider class, but let me drop it now. And if the symbol is from this subclass, then this condition of ellipticity is necessary, also necessary condition. Well, and now the Bessel potential spaces. Since we have integral differential operator, we have to consider Bessel potential spaces. And Bessel potential spaces, here is natural to consider the generic Bessel potential spaces generated by the generic differential operators. You take such a symbol, it's here, this symbol, as in usual definition of, well, you take this function as symbol, you take Fourier convolution operator with this function, this is Bessel potential. And this is, and the differential, well, okay, it will be clear a bit later. And then take this norm, Fourier transform of function, multiplied by this function, inverse Fourier transform, and norm in LP. This is the norm in Bessel potential space, generic Bessel potential space. And in the case when the S is integer, it is generic Sobolev space, which is such. You take generic derivatives, or all kind of generic derivatives up to order M. And these generic differential operators, and these norms of derivatives gives you norm in LP in Sobolev space, and it is equivalent to the norm defined above in the case of when S is, as in usual Bessel potential space. In this case, it's the same. Okay, and here you have again the theorem that it is invertible if and only if the symbol is elliptic, and if it is from the class PCP, then it is the condition of ellipticity is also sufficient for the invertibility of operator. Okay, now why we need all this and what it gives in applications. Here is the theorem about, okay, which I formulated already, about the invertibility of operators, unique solvability of convolution equation. Yes. Now the example. This example triggered all this work for me. It was Petrov from Petersburg who noted that if you take the transformation of the axis minus infinity, infinity to the interval minus 1, 1, and transform and convolution equations transform with this transformation to the interval minus 1, 1, then you will get interesting equations which can be applied for the investigation of very well-known equations. I will show you later. And okay, but reading this work, I noticed that interval minus 1, 1 is a Lie group under this operation, which is here, not sum, not quotient, not dividing, but altogether x plus y divided by 1 plus xy. Inverse here is, of course, inverse to x is minus x. Neutral element is 0 again. Yes, 0. And, well, and the Fourier transform is defined. Here is the Fourier transform. Looks a bit different, of course. And the inverse Fourier transform, the Haar measure is here. This is the Haar measure in this case. And the inverse Fourier transform looks this way. Here is the inverse Fourier transform, and here is convolution equation. This is the convolution equation on the interval -1, 1. And the Fourier transform gives the multiplication operator. And, well, and here you have full theory now. Well, you can define the symbol. Well, what Petrov had found, that these equations, which are listed here, Prandtl equation of the airfoil equation, integral differential equation, 014, also the trichomy equation, which encounters in the boundary value problems for the mixed type equations, and also the Lavrentiev-Bitsadze equation of the same Lavrentiev-Bitsadze equation. They are all the convolutions on interval -1, 1. So what was not available before, you can solve these equations precisely. I mean, they write the inverse operators in this case. And it is, I think, a very interesting work of Petrov. But after I found that the -1, 1 is the interval, so I developed the more general theory, how to say. And after that, we went further with my colleagues in Kent, Professor Różański, Duvan Cardona, and Hendricks. Cardona and Hendricks were his PhD students. And we developed, well, we found a lot of examples of convolution equations. A lot of examples of groups. Yes, Petrov and Suslina had found, just with the transformation, they have found that these equations were solvable. And Nugzar Shavlakadze also, trichomy equation, he also considered it with the same approach. He transformed the trichomy equation to the interval -1, 1. To the interval, to the axis, -infinity, infinity, and also solved it. It was parallel work. Okay, now why generic Bessel potential spaces are useful. If you consider boundary value problems for the Laplace-Beltrami equation on the surface, when the surface has angular points, Lifshitz boundary, so we reduce this problem to the model problems and investigate it in two different Bessel potential spaces, classical Bessel potential spaces, and generic Bessel potential spaces, because the equations boundary integral equations which emerge here, they are convolutions on half-axis. And so what the result was, here is the boundary value problem. This is the Laplace-Beltrami operator on the surface, and these are boundary conditions. It can be Dirichlet condition, poor Dirichlet, poor Neyman, or mixed type. And the Laplace-Beltrami operator, by the way, this is also, I am proud of these results also, that the Laplace-Beltrami operator can be written with the help of Günther's derivatives in such a very simple form, as a sum of the second derivatives of Günther's derivatives, not the usual derivatives. And well, since I have no time, I will not demonstrate how they are reduced to boundary integral equations. I will demonstrate only the result, the theorem about solvability. Well, we have three types of nodes where two Dirichlet conditions collide, two Neyman conditions collide, or Dirichlet and Neyman mixed type conditions collide. In these 3 points, you have different answers, different conditions for the solvability of equation. There's solvability also, Fredholm property and solvability. Yes, here is the model case. At every point we localize it, and at the angular point you have such a model problem in the angle. Yes. So here is the integral equations, and they are convolution equations on the half-axis you see here. And what is the result? I want to demonstrate the result. Yes. Here is the, you see, we in the generic Bessel potential spaces, we have such conditions. You see, the conditions on the parameters, conditions on, if these conditions are fulfilled, equation is Fredholm. And in some restrictions, they also, for some values of this parameter, which are found precisely, they are uniquely solvable. And more of this. We have found that the singularities at these angular points, they are also available with such approach. But if we consider them in the classical Bessel potential space, then we have difficulties of this type. Then the condition of Fredholm property is such this function does not be zero. So you can find it only approximately. The condition of Fredholm condition and the invertibility condition. That's in classical Bessel potential space. But in generic, you see, it was found by very, very explicitly. Okay. Examples. Now I will show you several examples, and we'll finish with that. Several examples of Lie groups. What we have done with my colleagues from Ghent Analysis and PDA Center, with Professor Różański and his colleagues, we have found these examples, found Haar measure, group operation, first of all, Haar measure, how they are defined there, character of these Lie groups, group of characters, then the Fourier transform, inverse Fourier transform, generic differential operators, describe the generic Bessel potential spaces for them, and well, and this all was done for such groups. Yes, angles, usual angular domain or angular domain with carved boundary. They are Lie groups, and even here it can be cuspidal point at the tip. Can be cuspidal point. What is very strange, here is the two-dimensional case demonstrated, but all star-like domain in Rn. They are Lie groups or star-like domains. So you can have their group structure, harmonic analysis, convolution equations, everything is available for the star-like domains. Also, that's actually the next examples are particular cases of the star-like domains. There's cones, pyramids, they are also Lie groups. Pyramids, double pyramids, simple pyramids, half infinite pyramids, finite pyramids, everything is Lie group. And even surfaces. Well, waveguide, carved waveguides, they are also Lie groups, and surfaces with Lifshitz boundaries, they are Lie groups. We, for the interval -1, 1 in power n, we have developed the full theory of pseudo-differential equations on these Lie groups, with Mikhail Różański, of course. And here's the literature, nothing special, but yes, thank you for the attention.
Thank you very much.